So I can no more estimate what my beta 2 and beta 3 would be in this model. All that I can tell you is that alright, using my two variable formulas, this is the value of beta 1 hat and this is the value of alpha. But I cannot tell you what would be within alpha, what is the value of beta 2, and within alpha, what is the value of beta 3 hat. Okay. Now, if multicollinearity is imperfect, so imperfect multicollinearity means that I no more have this relationship of x3 equal to lambda x2, but there is some more component, some stochastic error involved. So I'm saying that alright, my x3 is lambda x2 plus v. So, or x3 is lambda 1 plus lambda x2 plus v, where I can add up this lambda and v together and write it as one variable. So that means it is no more a perfect multicollinearity case but an imperfect multicollinearity case. Then although the regression coefficients are determinate, they will have very large standard errors, which means that the coefficients can be estimated but with less accuracy. So to explain this line, first of all, let's see how they are determinate. So instead of x3, I will substitute lambda to x2 plus v in the formula. So wherever I was getting x3, I would substitute this. So if you see this, I would get this, and if you further solve this out, it will come out to be 0. Right? Now the point is, so I'm assuming that this is 0. Why? Because there is no relationship between x2 and v. And how do I know that? So if you see a general model where I used to say that okay, y is equal to beta 1 plus beta 2 x plus ui, I was assuming that x and u are no way related. This was our basic econometric model. Now when I impose such a similar model in multicollinearity, imperfect multicollinearity, then I have this basic assumption in my mind that the stochastic error is no way related to x2 or the fixed non-stochastic term. So therefore this, which is summation x2v, here and here are 0. If you try solving, this is not equal to 0 by 0 form, and therefore I say that this is deterministic. But this will have very large standard error, and because it will have a large standard error, the chances of my t-test being accepted would fall. So if you see a formula, if you see it through formula, I have the following. I have t is equal to beta 2 hat minus beta 2 upon standard error of beta 2 hat. Now the standard error is very large. So if the denominator is very large, this entire thing becomes very small. So the chances of t calculated being less than t alpha by 2 for given degrees of freedom becomes higher. This increases. So the chances of not rejecting falls. So increases. So basically, for most of the cases, because standard error is high, t calculated would be less than t tabular, I will not reject my null hypothesis, and my null was that beta 2 hat is 0. So I may bring out a wrong interpretation saying that look, if I have a model y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ui, then x2 is not explaining y. I may get this interpretation because of this fact that beta 2 equal to null is not getting rejected, and this is happening because standard errors are really high. So I may get wrong interpretations. So now perfect versus less than perfect multicollinearity. In perfect multicollinearity, I have lambda 1 plus lambda 1 x1 plus lambda 2 x2 and so on equal to 0. So from here